Fyodorov's lecture yesterday, there were a few hands up. Gian didn't know this.
Yeah.
I
Apologize for
didn't
that.
know this. So I'm now delivering on my promise. I will sit beside watching you and the lecture. You paid for this. The purpose of this is to satisfy you, not to satisfy the lecturer. So you are entitled to ask your questions. And we specifically reserved the time to ask them and answer them. So I'm going to be firm on this. So please, if something is unclear or you feel that there's some discussion that could be helpful, raise your hand and we'll let you speak. And I'm sure that Leonid Pasteur will answer everything.
I'll do my best. Okay, just to finish, let me remind you that the main outcome of the last lecture was the definition, precise definition, what does it mean spectrum components, because the spectral analysis consists of, if you are in finite dimensional case, you have to find eigenvalues, eigenvectors, and you are finished. In a way, of course, you have to do the same in infinite dimensional case, but you have to distinguish different components, because as you saw, there are three components of the spectrum. There is absolutely continuous spectrum, there is pure point spectrum, and there is singular continuous spectrum. And spectral analysis consists, of course, in determining what is the spectral type of your operator, of the component of the spectrum. How do they could overlap, they could interact in a way. And as for pure point spectrum, it is clear, it is quite similar to the finite dimensional case. The only new feature is that it could be, in principle, dense. While in the finite dimensional case, of course, you have finite number of points, they are all isolated. So by using the terminology that I gave yesterday, in finite dimensional case, the spectrum of self-adjoint operator is always discrete, isolated points, because just n points. But in infinite dimensional case, pure point spectrum could be dense. Otherwise, it is already familiar for us from the finite dimensional theory. Absolutely continuous spectrum also not too surprising, because okay, the most known operator, just Laplacian, has the absolutely continuous spectrum. And in a way, despite that it is completely new with respect to finite dimensional case, it's not hard to understand. And in addition, this is quite a common thing in quantum mechanics, because all scattering problems, when you have your potential, which is roughly speaking, is concentrated in the finite part of the space, or decaying fast enough, the spectrum will be absolutely continuous, plus maybe some small, roughly speaking, number of eigenvalues, bound states. There is this third bizarre component, singular continuous spectrum, that, as I said yesterday, for the previous generation of spectral theorists was a kind of nuisance, because the main goal, for example, of scattering theory is to prove that this spectrum is just absent. Despite, okay, in principle it could exist, and our problem is to prove that it is absent. But in not random Schrödinger, but for Schrödinger operator, for example, with almost periodic potential, which I will mention a bit later, it's quite common. And moreover, there are very good physical models, so-called quasi-crystals, in which it happens that spectrum could be singular continuous. Physicists call this, sometimes call this corresponding eigenfunctions chaotic eigenfunctions. And the transport is quite strange. It could be proportional to the fractional power of the relaxation, Freemian time, etc. There is a lot of strange things. But nevertheless, okay, we have three components. Just to finish this topic, I have to mention several assertions concerning the stability of the components. You know, you have an operator, you made your spectral analysis, you found what is your spectrum is, but then, of course, you would like to know what will happen if you add certain, in some sense, small or just new operators to your operators that you already analyzed completely. And you would like to know to which extent the pictures that you already know will remain, or if not, what will be its change, yeah? And so the last point of the lecture, of the previous part, is stability of spectral types or spectrum component. These are synonyms. Okay, there is a collection of assertions of this kind, and they are still appearing, but we will need just few ones, and I'll mention them. The first is most classical. It's from the beginning of 20th century. It concerns the essential spectrum. Let me remind you that essential spectrum is a continuous spectrum, both singular and absolutely continuous, plus eigenvalues of infinite multiplicity. That means that everything which comes from infinite dimensions. Yeah, and this is it is, if I do not write the operator, that means it doesn't matter which operator, provided that it's self-adjoint. Therefore, the essential spectrum is stable with respect to compact perturbations. Okay, I have to say what is a compact operator. Compact operator is operator that you apply your operator to the unit ball in your Hilbert space, to all vector belonging to the bounded domain, and this set of vectors becomes compact. That means that you can select a convergence subsequence. The model, most known model of the compact operators, integral operator with continuous kernel on a finite interval, so best possible case. So roughly speaking, this is operator quite mild, quite weak.
Could you write the definition? What is it?
Yeah. Okay, please. Let me just a small insert. A is compact by definition. That means that convert any bounded set of vectors of your space in a compact set. The spectrum of compact self-adjoint compact operator is very simple. It's just it is discrete with a finite number accumulation points. This was done in the beginning of 20th century by Hermann Weyl. Next things that I'll need, in fact, I'm giving this section mostly because of this second assertion that I would like to make. That the absolutely continuous spectrum is stable with respect, because I'll use at least twice this, with respect to trace class perturbations. What is a trace class perturbation? It's a operator, it's subclass of compact operators. If you have a trace class operator, it has a pure discrete square spectrum. Multiplicities of all lambda are finite, and the sum of absolute values of eigenvalues conversion. It says, okay, if it would be, we know what is a trace in finite dimensional case. It's just sum of eigenvalues of your operators, counting with multiplicities. No? Here it is something like that.
So lambda prime is lambda?
Sorry?
You have a lambda prime and a lambda. Oh, that's.
Yeah, so it's trace class. And the assertion is that if you have that absolute continuous component remain the same, if you add to your operator with this component already present, if you add to this operator any trace class. This is famous Kato Rosenblum theorem. And let me give two more results because they are somehow nice. But don't be too optimistic that you can enlarge this class, because in a way this is optimal. Now I take the so if A, so let A is self-adjoint and B is Hilbert-Schmidt. This is another class, just with the same terminology. These are operators in which squares, sum of squares of eigenvalues conversion. It's a bit larger than trace class. Then A plus B has pure point spectrum. Doesn't matter what was the spectrum of A. You add to this operator Hilbert-Schmidt, a result will be pure point. For example, here it could be continuous. So it's just a bit stronger than trace class. Everything is. And
Do you mean pure point only, or?
Yeah, pure point only. This is again famous result by Weil, Hermann Weil, because there is.
If you take B equal to 0.
Just a moment. Sorry?
B equals 0.
No,
Come on.
He's saying they exist.
Don't ask me these questions.
So David Bridges
No, they exist. No, the statement. Okay. You would like to be precise.
Oh, okay.
Yes.
Very good. Now we understand.
Of course, I have to tune. No, it's clear that not anything possible. Yeah, there was a question or remark. Yeah. Thanks a lot. Yeah. And the last result that I would like to say.
So then agree, right? On the next, people can't
Just-
read the bottom of the
It doesn't. Okay. The last result to mention is the following one. It's a bit vague, but for generic orthogonal rank 1 projection P and again generic alpha real alpha pure point spectrum, better I will write epsilon. I explained it to you yesterday that you have to distinguish between the set of eigenvalues in pure point spectrum, because if the spectrum is if eigenvalues are dense, okay, it is still discrete set, but the pure point spectrum, it's a closure of the set of eigenvalues. It will be the interval, an interval. Therefore, so the set of eigenvalues of RA plus alpha P intersection with the set of eigenvalues of your initial operator is empty. So you have your operator that has pure point spectrum. For example, recall the operator n, just multiplication by this operator in L2Z, just multiplication by the coordinate. you have a discrete spectrum, equidistant, in fact, consisting of just of all integers, yeah? So you add to this operator a rank 1 perturbation, which is somehow generic, is not too special, and the new spectrum will be completely different. So pure point spectrum is very sensitive to the perturbations. And this, in a way, a bit later, I'll give you a very nice formula for the resolvent of this operator expressed via resolvent of this operator. And from that formula, you can easily prove this last assertion, while here it's a bit subtle. So what is it?
It will still usually remain pure point?
Yeah, yes. Just it moves.
It moves.
Yes. It's very unstable. In fact, you can move it quite easily by almost anything possible. Yeah. Okay. This is the end of this chapter. Next one.
The question here.
By stable, you mean the spectrum stays the same, or it just won't change size?
No, the both.
Yeah.
Okay. Now the next chapter that I would like, the abstract spectral theory is very nice things, but you can't work too long and too much in the abstract theory because, okay, it's too abstract. And the model, in fact, the model of all these results and much more is just the two classes of concrete operators, differential operators, infinite difference operators. We found first, I mean, we community spectral theorists and mathematical physicists, almost all phenomena that I discussed before and much more that you can find in any good book on spectral theory, they were first found as a rule in the context of differential or finite difference operators. So on one part, it is a very good model, and on another hand, it is best field to apply your abstract results. Therefore, this will be chapter 2. And let me see what I'm going to say you. The first is just a small introduction. The first section is just, let's call it generalities. Just, in fact, the notations, yeah? Okay, I'm going to, according to this title, I first just mention in passing just very shortly. I didn't write neither here nor here that I am about self-adjoint operators, but it is just by default. Starting from the very beginning, I am going to discuss only self-adjoint operators, nothing else. Differential operators. Okay, there is a general class. It's called better to say strictly elliptic partial differential operators. Let us write in the form that you have the in L2 in d-dimensional space, just corresponding differential equations, they have a form. I write in this form, not necessarily in this, but okay, d over d xk. This is my operator. So it's just the quadratic form of the partial of second quadratic form of partial derivatives with the coefficients that satisfy a condition. They are, of course, they depend on x. And the coefficient satisfies very important condition, which is known as a strong ellipticity. So you see, I have to assume that this is symmetric real matrix. I have to assume that it is the constant doesn't depend on x. For all x, we have this inequality. In particular, you can take as a matrix A a particular case
Should there be a bar on the?
Sorry?
Why is there a bar on the second side?
Okay, not necessarily, but better to write, to be sure, yeah. No, I'll tell you why. Because if you do Fourier analysis, d over dx will be I pi, and you have to be careful. Just because of that, not necessarily. Yes, and the particular case, of course, particular case, just the operator, just Laplacian. But according to my terminology, I have to write continuous Laplacian. Yes? You get this operator just taken as simplest possible, just matrix, unit matrix. You can, of course, consider a bit more general case. You can add here. This is the most important part, differential part. You can add here, of course, the potential. And the particular case of this operator will be very important. Continuous Schrödinger operator H minus Laplace plus V. I do not discuss, nor here neither here, the domain of definition. It is quite subtle for the differential operators to find the domain of definition of this operator. Okay, it includes a lot of things, harmonic analysis, Sobolev spaces. Don't think too much about that, because we will not discuss. Huh?
What's C?
Anything. Any complex X for any condition.
So for any collection of n complex numbers, you have to have this inequality. Yeah.
This is an example of a strictly elliptic partial differential.
Sorry?
And what you're writing here is just one example, right?
Yeah, of course. I do not write.
Higher order.
Yeah, there are higher order strictly elliptic operators. There is a notion of strictly strong ellipticity according to Petrovsky, which concerns of any even order. And there are examples. For example, if you study the oscillations of the plates, it will be a fourth order equation. Therefore, you have to do a spectral analysis of fourth order. But I am just, I am about examples. I am not pretending in any sense that I am doing a kind of exhausting classification. Not at all. Just examples, yeah? And the most important, I repeat, for us it is most important example is Schrödinger operator. And now let me pass to second class, finite difference operators. And of course, no, I didn't say that the matrix could be symmetric, but if not, it will be symmetrized just by this form of writing. So for we are about finite difference operators in L2 ZD now. Yeah, how do I define them? I'm considering a function A which acts from ZD times ZD complex valued function of two discrete variables, yeah, just a, x, y, which satisfy the properties. This property and okay, and let me see, and not to be too general, of compact support. So it is 0 outside of certain product of certain domains, yeah? And then I define my operator as just matrix operator. In one-dimensional case, well, what is it, by the way? It is just the matrix, and you have a certain band near the principal diagonals where you have something not zero, a is not zero, and here you have zeros. This is finite difference operator, and the okay, excuse me. Yeah, and of course, the simplest example is again just like here. Now I'll give you discrete Laplacian. The same notation, only without. I do not write minus. We discussed already that. Very simple operator. You take your function, and now you do the all neighbors, nearest neighbors, you take some. Yes?
If you want to have this, the dominant diagonal structure might be the symbol should depend on the difference.
Sorry?
Otherwise, you only have some finite block of your matrix, right?
Sorry? Yeah, you're right. Thanks. So this function is 0 if the difference of its two arguments is bigger than a certain number r. This is my, okay. In one-dimensional case, b is 2r plus 1, as far as I remember. So you have just a, and this is the simplest case, which is already quite interesting. This is discrete Laplacian. I repeat, it is just like that in one dimension. Case, it will be just and again, it's a simple thing. And now I am writing discrete. This will be my notation. SO, Schrödinger operator, discrete SO in dimension 1. It will be just the operator H acting by the formula. You have a real valued function on the lattice, on the chain, yes?
Just want to make a remark. So you're taking the diagonal out of the Laplacian because you can put it in the B.
Yeah, yeah.
We discussed it yesterday.
Oh,
the
sorry. Okay.
funny Laplacian.
Yeah. No, it is just, you know,
To do this.
not to write every, look, just it's a trivial economy, you know. Yeah. And, but one of the, I see as one of the goals of my course to give you a bit of jargon of modern spectral theory. So this is a part of jargon. Yes, we have this operator, and in this case, quite easy to say what is the domain of H. it follows from general principles of the spectral theories that the domain is the set of size such that so if your potential is bounded, this is just L2. If not, you have to be just a bit careful, but it is not in any way serious restriction. Nevertheless, to be precise, I just have to say this. So it is more or less what I would like to say about in this for generalities in the first section. Now I would like to come to the second one, which is important for me. So starting from this moment, I'll speak only on one-dimensional case. I leave multidimensional case to the lectures by Tom Spencer, which is, I think, which contain a lot of new things. But my goal, as I said, is in a kind of introduction. I'll try to explain you on the simplest possible technically case, main ideas of localization theory. And this simplest possible case, it is here, just one-dimensional Schrödinger operator. Now, but before to come to start to speak about random potential, almost periodic potential, I need a piece of spectral theory. By the way, rather old. It's beginning of 20th century. It belongs again to Hermann Weyl, one of the founding fathers of the spectral theory. It concerns the second order differential, finite difference in differential equations, in particular this operator as well. And I'm going to present you a collection of formulas that very special for this case of second order finite difference operator, but that are quite efficient, and they allow us to prove localization, okay, in one page, being prepared to that. And this is the main point of the preparation. What is it about? Okay, Weyl theory. Let's take, I take the interval. I take two integers. Now I am on the lattice. My intervals, my points, everything on the lattice. I have 2 points, to be absolutely precise, finite points. I denote b minus a plus 1. It will be n, and I will assume somehow that it is big enough. Don't ask me what will happen if I have 2, 3 points. I am going to make, in fact, the limit n to infinity. But I would like to start from, this was the intention of Weyl. Let's start from finite dimensional case. Let's try to construct what does it mean, all these infinite dimensional operators, and which kind of formulas, which kind of spectrum technique we can develop for that. And the idea was, despite that Hermann Weyl was one of the greatest mathematicians of 20th century, the idea was completely physical. Let's start from finite interval and try to make limit when interval tends to infinity. And we will do this in 2 steps. First step, we will work on the semi-axis. I'll fix, say, A, and I'll try to make B big. And then you'll see that the 2 infinity is already much simpler. So I start from finite dimensional case. So I would like to consider the operator, which is, I'll denote H, A lot of notations, but just for a while. So it is just the matrix, n by n. N is here. Just Schrödinger, but not on the whole axis, but just on the interval. Yeah, excuse me. Yes. Okay, I'll write first here. It will be a bit strange now, then I explain. Now I go to the end. Here I write V on B plus cotangent beta. Here I write here unities and 0 everywhere else. So you see, you have in fact, if you do not look on the first row and last, you see just the Schrödinger operator, just a section of the Schrödinger discrete Schrödinger operator. What are these strange things? It comes in fact from classical mathematical physics, because I would like to write a kind of boundary these are a kind of boundary conditions which becomes clear if I'll write you a bit different. Now I would like to write not in the matrix form, but in the form which I would use if it would be differential operator, because I would like to make a parallel. Yes, so I write the following: alpha, beta, these are here, AB on psi on x is psi x plus 1 plus psi x minus 1. These are these unities, yeah? Plus V on x. This will be for all x between and now I write boundary conditions.
V of x times psi of x.
Sorry?
V of x
yeah.
times psi of x.
Thanks a lot. Yeah. Say psi a on cosine alpha minus psi a plus 1 sine alpha is 0. Psi b cosine beta minus psi b plus 1 sine beta is 0. This is, I repeat, you have your operator is given by this formula, but if you don't want to write matrices, you can look in that, and when your b is x is b, you have a b plus 1, and you exclude b plus 1 by using this equation.
The potential in the last equation.
Sorry? No, there is no potential. Of course, it's boundary conditions.
But if you look at your matrix, you wrote there.
Okay. If you like, in that way. No, stop. Everything is okay. Everything is okay. I take x equal b. It's allowed, yeah? X equal b. Here is no potential. I would like to live on the interval a plus 1b. But if I would like to write boundary conditions in this form, which is, let me remind you that if you take any book on classical mathematical physics, you'll find your operator just for the moment. You find the definition will be like that. The operator, by the way, the continuous Schrödinger. By the way, Well made his theory first for continuous case, and then Hamburger remade. You write like that: psi 2x plus Vx, x between b and a, and then you write psi a cosine alpha plus psi prime a sine alpha is 0, and psi b cosine beta minus psi prime b sine beta is 0. You have to write the equation in boundary conditions.
Presumably, then you should delete in your matrix the upper left element with v and the.
Why?
Because if you apply your matrix to the function.
I'm living on that interval. These points are not present. I don't understand what is going on. You take the vector psi a plus 1, etc., till plus b, and apply. This is all. I'm living in that space. Okay, so it is a motivation, I repeat, because This is known as a Sturm-Liouville problem, and it comes from the middle of 19th century. Okay, this is but I would like to present it in the form of finite dimensional, just linear algebra. You have a family of finite dimensional, just matrix. It's called Jacobi matrices because you have only 3 non-zero diagonals. With okay, there are coefficients. There is potential, and there are 2 parameters, alpha and beta, that place, as we see from that form, place a role of boundary conditions for your equation. It's not necessarily to write, but you can write it like this. You're not necessarily to write in the form tan alpha, just a constant. Because if I have to mention, of course, that alpha and beta, they are both here. Okay, this is our operator. How to find eigenvalues and eigenfunctions? Of course, you can't find it explicitly for any potential, but nevertheless, you can write quite efficient formulas. For that, you have to introduce some nice things that it will be also used by Holtscheid, Cauchy solutions of my equations. These are, I will denote them y, x, lambda. X is z, lambda real valued. So these are solutions of the same equations. I have to write x plus 1 plus y x minus 1 plus vx yx equal to lambda y x and the condition y a plus 1. Okay, maybe from that point, let me take a is 0 and what is better? Yeah, I'll take a0. Therefore, I write here a0 is sine alpha, a1 is cosine alpha. So it's just definition. It's called Cauchy solution of my, you have a finite difference equations, in a way the recurrence relation, and you see, you know y naught and y1, and then you go by the equation. Because if you take here x equal 1, you see, you will have here 0, you know, here 1, you know, 2, you find, etc. Therefore, the solution, the Cauchy solution always exists. Unlike, by the way, the spectral problem. I don't know whether the solution of that problem is exist. A priori, of course. So, but I would like to construct this solution. So I use the Cauchy solution. What is the advantage? I know that this function of 2 variables, one is integer and second is just real variable, that this function exists. In fact, it's easy to see that it is a polynomial of order, as far as I remember, x minus 1. Because there is lambda here, and when you make iterations, the powers, the degrees of lambda will accumulate, but for any finite x, it will be polynomial in lambda. And okay, this is nice thing. And now you see that this solution always satisfies the first boundary condition. So our concern is on the second boundary condition. Okay, I'll write the second boundary condition now. Yb, now I write lambda explicitly, cosine beta minus y b plus y sine beta is 0. Let me write explicitly. And what is it? It is polynomial with respect to lambda. Alpha and beta are parameters, fixed parameters. Fixing alpha and beta, we fix an operator, because in fact we have two parameter families. And okay, you have, and the solutions of this equation, lambda L are evident eigenvalues of our operator. Okay, we have a polynomial of the power of the degree n. There are n roots, n zeros. The only problem is whether they are real or not. Yeah, but they are real because by general principles we know that if you have a Hermitian matrix, you see it is symmetric, that eigenvalues are real. Therefore, we know a priori that all zeros of this polynomial are real, and they are nothing as eigenvalues of my operator H A alpha beta A B. And how to construct eigenfunctions? Simple. We have already. This is already. If we take here if we take in the Cauchy solution instead of arbitrary lambda L, this will be eigenfunctions because it will satisfy the equation. H alpha beta A B y is lambda L y. Yes? For lambda equal lambda L. So we constructed eigenfunctions starting from the Cauchy solutions. And the only a minor disadvantage that in spectral theory the good manner is to work with normalized eigenfunctions. Yes? So I have to, this eigenfunction is not normalized in principle, so I have to introduce the things which I'll call NAB alpha beta on lambda, which is just the sum x from 1 to n y square x lambda. And then my normalized eigenfunctions. Oh.
Move it up.
Will be just psi L on x will be just y x lambda L divided by this. My definition will be the square by n alpha beta A B on lambda L. Moreover, I can write immediately the resolution of identity of this operator because I am in finite dimensional case. Alpha beta A B. You see, resolution of identity, what is it? I remind you that what is it? It is just the operator valued measure. Yes? And but for fixed interval, this is just projection orthogonal projection. And since we are in finite dimensional case, of course, it's certain matrix. And I'll write this matrix, x, x, y. And now I have to remind you that it is measure, therefore it is a function of interval. And the definition is very simple. Sum lambda L belonging to delta. Okay, psi L on x, psi L on x prime. This is a general definition of the resolution of identity, but in our case we see that it is nice formula. It is just the sum lambda L from delta y x lambda L y x prime lambda L, and here square of normalization. Now I can continue. You see, no, I have to write here. Okay, let me write because it is important. Alpha beta 1 everywhere 1 b lambda L squared. Now introduce a function. Now we introduce a function which called the function spectral measure. It is a kind of measure, but now it is just scalar measure. Alpha again 1b alpha beta on delta. The definition like that: lambda L from delta, and here just the normalizations. N alpha beta 1b minus 2 and here lambda L. Everything is just a bit different form, standard formulas of linear algebra. But now, just using this measure that I just introduced, I can rewrite my principal equality here, yes? In which form? I can write that E1b alpha beta on delta is the integral y x lambda y x prime lambda, and here rho alpha beta 1b d lambda, because it's just atoms, just delta functions in these points. But what is the point to do this? The point is that we have now formula that is more or less written in the form in which the parameter b that we are going to send to infinity a bit hidden. In fact, it is written in very convenient form. What is the problem to passing to the infinite interval? Let me remind you the operator, the 1D periodic Laplacian that I'll give you on the first lecture. I gave you in the first lecture. This is operator of the form 0, 1, 1, 1. Here are zeros, here ones up to here, but there is one here, one here. By the way, it is not, you can't describe this operator by the conditions written over there. It's a bit different, but nevertheless. And you remember that we found that eigenfunctions of these operators are just the Fourier exponents. So spectrum is the spectrum, I remind you, 2 cosine 2 pi L over n, and the eigenfunctions corresponding just 1 square root of n normalized, e to the 2 pi I, of course, I L x over n. And if I would like to make the limit n to infinity, I am going to obtain zeros for eigenfunctions at any finite fixed point x. This is a trivial but problem. We can't pass to the limit just directly. Roughly speaking, and we understand what is the reason for that. Normalization factor. Because of normalization. We normalized our eigenfunctions by the norm 1. And this is good, of course. But we understand. But since we found that in infinite dimensional case there are eigenfunctions that do not belong to the space, it is not a good idea in infinite dimensional case to normalize our eigenfunctions, because the norm could be infinite, like here at the limit. Therefore, I have to pass to solutions I have to renormalize my eigenfunctions. Of course, in general case, in abstract spectral theory, it is impossible. You have not sufficient amount of analytical information. But for concrete case, like here, you can do this. And you see the idea is very simple. I just included this normalization factor in the new measure. And we see from that formula that when tends to infinity, eigenvalues, they are more dense and dense. And you fix an interval, and you will see that there will be more and more atom in that measure, and you hope that everything will be okay, because at least intuitively you see no problems to pass to the limit. It's reasonable action to do. Yes? Okay. Now I have nothing to see that to say you that it can be shown, because it's a bit that as b tends to infinity, there is the weak limit. So rho alpha beta 1b limit n to infinity, there is a certain measure which I will denote h rho alpha plus, not h but b. This is the result of the theory. Unfortunately, I have no time to prove it. It's about a lecture to prove this. So there is a measure, limiting measure, and okay, there is a point that I can't formulate good. And if I know a priori that my operator H is self-adjoint, for example, if potential is bounded, that limit doesn't depend, and if H is SA, rho, the limit does not depend on beta, on the second boundary condition. It's intuitively reasonable. You see, you send B to infinity. It seems that the dependence on B should disappear, and it is in fact disappearing if if potential is not bad enough. What does it mean? I will not discuss, but just to be satisfied that says potential is bounded, no problems. There is no dependence on beta. Yes.
You should stretch that the right hand side also depends on delta.
Yes, thanks a lot. Yeah. Maybe I do better. Just because I said the weak limit, let me remind you what is the weak limit of the measures. Weak limit of the measures is the convergence of the measures on any interval whose points are not atoms of the limit, because it could be atoms we discussed already. Yes? And there is certain property of total mass which I do not discuss. Just this convergence of the measure on intervals whose you have already the limit thing. You see that a sequence of measure is a limit of that measure if the convergence of all interval delta whose endpoints are not atoms. Okay, and since you have this, you can pass to the limit. You see, the dependence on B is only here now. If you are able to prove that this limit exists, you pass to the limit under integral sign. There's corresponding theorem that allows you to do this. Okay, and you'll get your operator on the semi-axis, nicely defined. And this is a definition. So the limit, now you have resolution of identity, it corresponding operator, and we have an abstract theorem saying that resolution of identities in self-adjoint operators, they in one-to-one correspondence. So we have a limiting resolution of identity, which I now depends, which I will denote plus x prime delta is integral. By the way, am I right here? So we have, since the Cauchy solution, now I write everything depends on alpha. We have resolution of identities, and of course, we have our operator. I have a matrix of my infinite operator. Everything is well defined. And I would say that you remember when I has been discussing the finite dimensional case, I gave you two forms of the spectral theorem. One form, just the sum of projections multiplied by eigenvalues. And second form is just, I called it coordinate form. So this is a coordinate form of Schrödinger operator on the semi-axis with the boundary condition and 0. So the operator is given h psi on x now. And you write here, to be correct, you write that psi 0 cosine alpha cos alpha minus psi 1 sine alpha is 0. So this is what I said at the beginning. I said to you at the beginning that the operator is usually given by its matrix, and the goal of spectral analysis to find eigenvalues and eigenfunctions. And we see that for this particular case, the spectral analysis is here. You can always construct these solutions. Cauchy solutions, you need to know anything, just do iterations. And then, of course, there is a subtle thing. There is this measure, okay, but this is where everything is hidden, all spectral analysis. There are some methods to find, but sometimes yes, sometimes no, depending on conditions. But at least we know now what is the coordinate form, because this abstract form via projections, it's very nice, but it's not too efficient. You can't do too much with that. Here you have absolutely concrete things. Everything is, even you can do many things, even do not knowing the measure. This representation, integral representation of the resolution of identity and the operator itself is very useful, even if you do not know the measure itself. You'll see soon that we, in fact, by using these formulas, we can find we can, for example, conclude the measure is pure point, the spectrum is pure point. All the spectral information is here.
So can we pause for a second and just summarize? Can I try to verify whether I understand? Following while, we introduce this auxiliary H depending on alpha and beta.
No, this is this is Sturm-Liouville. This is also,
Sturm-Liouville.
it's classics, you know. No, you start from the problem in a finite interval with it's called separate boundary conditions on
Right.
each.
And so we put in two parameters.
Yes.
Parameter alpha
Yes.
turns out to be important. It's still present in the final formula. The parameter beta seems to be less important. Maybe we can even neglect this.
No, when you are at finite interval, you have to write something. Otherwise, the problem is not well defined.
If I want to go to the infinite dimensional case, to the limit n going to infinity, you're telling us that the dependence on beta disappears.
Yes, yes.
So as a practitioner, you know, as a physicist, I usually want to compute.
Yeah.
Maybe the best way is to not use beta. You use
No. As you see, as the limit form, there is no beta. So if you tell me that I am about to work with self-adjoint discrete Schrodinger on the semi-axis, don't mention beta. It doesn't exist. It is just the way to construct. You know, just the construction. Since you construct your infinite dimensional operators via limit on finite dimensional things, you have to put a bit more than you need.
But where do I need to use the beta?
In the proof, of course. You need to use beta just to write finite dimensional problem. Just to write the problem in finite dimensional interval, you have to write. You have no choice. Otherwise, the problem is not defined. If you do not fix boundary condition on the both ends, you will not find eigenvalues. You have nothing to start.
Can't I set beta equal to pi over 2?
Please.
And then there's nothing. The cotangent.
But in that case, you will not know that the result does depend on beta.
Well, you proved that for me. And
Okay.
I'm
If
a
I
physicist, I just want to apply
if-
it. I believe that your theorem is correct, and once it's
no questions,
established,
please.
that beta
This I allow you to do. No questions.
Okay, so and then we go through the Cauchy solution. That is clear. It always exists because it's just an iterative scheme. The outcome are these functions y. We normalize them. Then you write the formula for the resolution of the
Identity.
It has a normalization factor. Then you write spectral measure. At first, it's not clear to me why this is the correct formula for the spectral measure. But at the end of the day, it's clear that you go to this formula, and then I understand. 1 over the sum over the lambda L in the interval of the inverse square of the normalization is the spectral measure. If we don't see that a priori, maybe you know that a priori, but certainly at the end of the day, it's clear that this is so.
But you should see also that it is the spectral measure at the finite level because it's the sum of projections onto the individual eigenvalues. It's written in there.
Just in coordinate form, yeah?
Yeah,
Yes.
he's written each product of psi at x with psi at x prime is really just the projector
Yeah.
after you normalize it onto the eigenvalue lambda.
No, I repeat, the problem is described, in my opinion, here is a good good example to see what we have to do, starting from finite dimensional case. You see?
Yeah, can you show how you take this example and you go to this whole machinery and you get what we are using?
No, this example is not good. I'll give you another because here the periodic case, no, periodic case is not included, in fact, in this theory. This is a special thing. Because in periodic case, what are boundary condition in periodic case? You write psi naught equal psi 1. So one. Psi naught equal b. Yeah. So you relate the values of your solution on two intervals, while here it is a simpler, I'm choosing the simpler case. Here is another example.
I can choose also other
Stop.
boundary conditions.
Wait.
and-
Another example. So example. So it's called 1D Dirichlet Laplacian. It is a matrix of the form. In fact, this is 0 case of my formula with potential 0. So it is 0, 1, 1, etc., etc. So this one, here 1, 0, infinity. Everything. So you have semi-infinite operators with ones on the two diagonals next to the principal, and everything else is 0. Yeah? And why I called it Dirichlet? Because it corresponds to alpha equals 0. So it's, if alpha is 0, you have to, you see that it is boundary condition is psi beta is, psi a is 0, which is, by the way, here. Yeah? Otherwise, I would have here the tangent, yeah, but I have no. So it's easy to find that the Cauchy solutions here, x lambda, v is 0, is sine x theta over sine theta, where you can find. So I write lambda in this form, and the spectrum is minus 2, 2. Just verify. So you see, your y naught is not, it is just, okay, this is a function. It is 0 at 0, as it should be. If you would like now to consider the finite dimensional case, you have to put, now is beta should be pi over 2. So your condition is just sine b theta is 0. And you find that the theta L is pi L over b. Now if you do carefully all these calculations, all the limits, you'll find that your measure how to write it? V equals 0 is just 1 over pi. And to do this is good exercise. Just take any, so it is a derivative, yeah. So the measure is, spectrum is absolutely continuous, by the way. The measure is, as you see, because the measure has a density, and it is concentrated, of course, on the spectrum. Corresponding solutions are like that, but they are not normalized because this function is a function of x. If you take the square and that sum over x, the integral will be convergent. You remember I mentioned when we started to discuss the infinite dimensional operator, I said that the most important new phenomenon in infinite dimensional case that There are somehow eigenfunctions that do not belong to the space. Our eigenfunction, in a way, doesn't belong. We still do not know what is it, but nevertheless, we know that everything is okay. We made the limit. So it participated in the integral presentation of your operator.
So physics-wise, it's clear. Now, what is the mathematics of an eigenfunction that does not belong to the space?
Okay, this is what I would like to say just now. I would like now to say, just by using all these things, I would like to introduce the notion and this will be, so the next things to define, it's called generalized eigenfunctions of a 1D Schrödinger operator. In fact, multidimensional case is the same. By definition, these are solutions of the equation H plus alpha psi for lambda this is definition. So these are solutions, not necessarily, in fact, they have to satisfy the boundary conditions, but okay, the solutions corresponding equation, yes? Okay, I have to write psi 0 is cosine alpha, psi 1 is sine alpha. So this is all. This is my definition. So these are solutions. You are dealing with finite difference equations or differential equations, absolutely practically the same result, and even the form of the result is in continuous case, a continuous Schrödinger operator. You have the solution of your equation satisfying your boundary value problem. It has to be solution. First, it has to satisfy boundary condition. We have to take our parameter, but it is a solution of the equation with a parameter. The only things that we have to take care of is that the lambda should belong to the support of spectral measure. That means that we take only those solutions that participate in integral representations of the resolution of identity in the operator. This is all. And now, to finish, the last section is the so this is section 3, yeah? First was generality, second divide theory, and third is polynomial bounded of generalized eigenfunctions. I'm going to present a very simple fact that for many years somehow it was known from 50s, but somehow till the advent of random Schrödinger operator was a kind of vignette in the spectral theory. It was just okay, just a result. But even when we started to do spectral theory of random Schrödinger, we understood that it is, despite that it is very simple, you are going to see it is extremely important thing. And okay, what we are going to do? We are going to prove the following. That okay, I will be in concrete context. This is my, in fact, theorem. So generalized, yes?
But in your definition of generalized eigenfunctions, I think you also have now included the eigenfunctions that are exponential growth.
No.
Which do not.
No, here, yes. But the statement that I am going to prove excludes this. In the definition, yes.
Yeah,
Yes, yes, but try to find. Show me one. I assure that you can't show. Because there is a condition which is very hard to verify.
I mean, they do not.
No, I mean, everything is written here. Generalized eigenfunction, these are solutions for lambdas that belong to the support of the measure rho.
Excuse me, what do you mean by rho plus?
Support?
What do you mean by rho plus 8?
This is what I'll explain, yeah.
Okay.
I'll explain. So, there are a bit more detailed form of this assertion. So I say that generalized eigenfunctions for any lambda, for almost all lambdas with respect to this measure. This will be standard notation, almost everywhere in lambda. I have a measure, doesn't matter which measure I have. If I write that MAE, that means that I am doing the assertion with respect to this measure on the corresponding parameter. So I say that for almost all lambdas with respect, you have a measure. If you have a measure, you have a notion what is the set of full measure. I am saying that the set of full measure with respect to lambda, there exists for every lambda, almost every lambda, there is a constant depending on lambda, but not on x, such that we have this formula where a is any number bigger than 1/2. But it could be arbitrarily close to 1/2. So roughly speaking, we allow to generalized eigenfunction to grow if yes, not faster than the square root of x. No exponents, as you said. It's impossible. If lambda belongs to the spectrum. This is a fundamental fact. So in fact, classical mathematical physics.
Smaller.
Huh?
No,
bigger.
A can be arbitrarily large in your.
Please, but I need only bigger than 1/2. Of course, I'll take this minimum possible. Okay, Jan, I'll write better. No. Maybe it's psychologically better to write in this form.
No, I understand.
You can take whatever you want, but yeah. So this is a modern. So there was a certain activity in spectral theory around this assertion because there was one of the important people in classical mathematical physics, Vladimir Steklov, Russian mathematician. By the way, he was a professor in my town, Kharkov, for many years. He made a conjecture that generalized eigenfunctions it was different language in that time. It was the beginning of 20th century. Generalized eigenfunctions abounded. Okay, it is not correct. If we say just this short form, it is not correct. It was proven, by the way, about 10 years ago already. But there is a weaker statement which is certainly correct, which I give you. But for many purposes, you are going to see it's already sufficient. Because, thank you very much for your question, because it excludes exponentially growing solution. And it will be important for me. I will use this fact that you can't find generalized eigenfunction that grows faster than, say, x to the power 1/2 plus 1 million, 1/1,000,000. Okay, I have just 10 minutes to prove because it's very simple fact.
So we are still on the half line. Are we ever going to get to the full line?
It will be at the beginning of next lecture.
Okay.
Yes. So we are still on half line. Yes. But now, what about now? I would like to write the integral representation for the resolvent. But it is just a function of my operator, and I know how, since I know resolution of identity, I know how to write any function. So it will be just integral 1/λ minus z, and here, okay, let me write once more. Now, I would like to take a particular case of that integral representation of that formula. I put x equal x prime and z just I. And I take imaginary part of that formula. Remember that lambda, we are integrating over real line, in fact not real line but support of the measure, but it is automatic. So lambda is real, x is real, this solution is real. Taking imaginary part, we have to take care of only of that factor. And by doing that, we obtain the formula
How did you get G?
Sorry?
How did you get G?
I don't understand.
G.
How did you find?
Yes.
Because I know by definition the resolvent is H. This is a function of H. And since I know you remember we had a general formula G on A,
Formula was written yesterday.
integral G on lambda. Okay, this particular case, so I have that imaginary part of GH alpha plus XX y is the following thing, just 1 over lambda square plus 1, and here y alpha square x lambda rho alpha plus lambda. Now we have a general fact. Recall that if you have a self-adjoint operator, doesn't matter, abstract one, so you have the bound. In fact, we derived the bound. This bound was proven because it's trivial. So in particular, what is it? You can. It is just GH alpha plus. Yes, you take the vector, which is just a unit vector concentrated at x, and then you write. I am writing the definition of the matrix. Yeah. So what does it mean? It means that the absolute value of these things of I is not bigger than 1. Because I took as z, I took just y. Yes? So I know a priori from general theory that this is bounded by 1. So I just repeat. I take that and I plug here. So we have this inequality. Yes? Now, what I do with this inequality, I will multiply by 1 plus x to the power a squared. A is from my theorem. And since a is bigger than 1/2, the series from that function convergent, yeah? So if I multiply this equality by that function, I'll get here finite thing. So I can write that the sum x from 1 to infinity, integral 1 lambda square plus 1 y square alpha xy rho plus alpha d lambda Now we are dealing with positive functions. It is known that I can interchange the infinite sum and the limit.
One should be some constant, right? Some of it.
Yes. And since it is just a theorem from the measure theory, if you have integral, you have a sequence of functions depending on x, and you have their sum and integrals. You can interchange integral and sum. So I get from that the series x is called Beppe-Levy theorem. That the series of y square x divided by 1 plus x. Okay, excuse me. I made a very strong mistake. xa squared. Xa squared yes, I can write this formula. X lambda. So I can write, I repeat, it's just a theorem from the integration theory called Beppe-Levy's theorem, that we can deduce from this equality the finiteness of the integrand, but for almost all values of integrating parameter. Okay, since the series is convergent, its terms are bounded. This is what is written there, nothing else. So you see, it's a very simple thing, very simple observation leads to quite serious conclusion. That generalized eigenfunction, despite that they could not necessarily decay to be square summable, they can't grow too fast. This is why the theorem is known, the result, the property is known as the polynomial boundedness of generalized eigenfunctions. Okay, it's a good time to stop.
We will use a few minutes that we have for questions. Actually,
We had 90 minutes for questions. In fact.
Yeah, we've used quite some time for questions, but we have some time left. Actually, I must say, you made a serious mistake and then corrected it, and that actually I can't quite follow anymore how the reasoning.
Martin, it was not a mistake, it was misprint.
You said it was a mistake.
Yes. Yes.
So we start with the formula for the imaginary part of the Green's function of H alpha plus.
Yeah.
So this we understand. Then you multiply
by this function the both sides of this inequality, and I made the sum with respect
so
to
you
x.
multiplied on one side. You should also multiply on the other.
No, but I wrote here the bar. It means that I multiply the whole. This is my notation.
You know that exists.
Oh, you multiply both sides. Very good. Okay, that helps. And then
Now, what I do? What I
Then you
did?
sum.
I wrote this inequality.
Constant.
I derived this inequality. Then I multiplied the both sides of this inequality by this function. In fact, this is a sequence, yeah, because it's discrete. Is summed over x. Of course, the both sides. And I got here, and here I got a constant. What is a constant? In fact, this is a sum of this series, yeah?
okay.
Okay, and then simple observations that you can, since you know that the sum of integral, the series from integral is convergent, the series itself is convergent, but for almost all values with respect to the measure. This is all.
What was the name for that theorem that you called?
Beppe-Levy. Oh, I don't know, either why or this. I think it's Italian. I think like that. Is Italian. So it is just the standard theorem of integration theory, which, okay, I can't explain. But intuitively it is clear, because since all functions are positive, there is no cancellation. Therefore, if you have a convergence of integrals, we have no choice. The summands should be the series. You can interchange the integrals and the sum. This is all.
Very good. So generalized eigenfunctions.
Are polynomially bounded.
Period.
And this is, okay, just to conclude that this is a very general fact. This is valid for all the axes. This I will mention next time. This is valid in multidimensional case. This is valid for differential operators as well. So it is quite general, and you see simple fact. If I would prove it if I would start to prove it in continuous case for differential equation, it would be technically harder, because the point plays much smaller role in the. For example, I couldn't use this because the point is not delta function in continuous case is not a vector. So you have to take care of the resolvent, of the kernel of the resolvent. It is not always existing. You have to prove that the resolvent is integral operator. There is a lot of work which is sufficient to write a book, just to have this fact. This is why, by the way, I am doing discrete case. Differential equations.
But the bottom line of the
The
statement.
the bottom line, no. I mean, the final assertion is the same. There is a very nice book. Unfortunately, this fact, maybe just because it was considered by spectral theorist community as not too important, is well explained not too many places. I know the one book, I'm happy that this book was written in capital of Ukraine, Kiev, because this is why I know it's quite well. I know the person. This is Professor Berezansky. There is a book called Eigenfunction Expansion for Self-Adjoint Operators. It was written in the 60s, translated by the American Math Society. It's completely accessible. And there are 3 chapters of this book. In fact, this is one of the main results, in which he explains quite in detail all these polynomial bounds for finite different differential operators, etc., etc.
Very good. Let's break for coffee.